Welcome to Math TV with Professor V. We had a request for more examples for Calculus 1 curve sketching. So if you haven't seen the first video lecture, I'll link it here where it goes through more introductory examples. And then now we're going to dive into exponential, logarithmic, and trig functions and going through all of the steps for curve sketching. Okay, so let's start off with nice little logarithmic function here. We've got y equals the natural log of 12 minus x squared. All right, so I'll remind you what all the steps are. First step, we are going to find the domain. So the domain, let's think here. When we have a logarithmic function, we know that the argument cannot be negative. So what does that mean for us? That means that 12 minus x squared has to be greater than 0. Anytime you solve a non-linear inequality, you got to be super careful, okay? A couple ways to go about it. You could test intervals on the number line using the zeros of the expression on the left-hand side of the inequality. The zeros are going to be plus or minus rad 12, right? Another way of thinking about it is, we know the graph, y equals 12 minus x squared, that's just a parabola shifted up 12 units, and the x-intercepts are going to be at plus or minus rad 12, or 2 rad 3. Okay, this is just so I can solve this inequality. And if I think about this graph, I'm just doing a rough little sketch here. The solutions to this inequality are going to be the values of x for which that parabola lies above the x-axis. So we can see clearly it's this portion here in the middle, or basically when x is between 2 rad 3 and negative 2 rad 3. Now, how would you solve it if you didn't graph it? Well, then you would take 12 minus x squared, find the zeros. Maybe you remember doing it this way instead. So the zeros would be where x squared equals 12, which means x equals plus or minus 2 rad 3. Then you make a number line and you test each of the intervals. You have 3 intervals to test here. The first one would be from negative infinity to negative 2 rad 3. The next one's from negative 2 rad 3 to 2 rad 3. And then the last one's from 2 rad 3 to infinity. And you're testing in 12 minus x squared what the sign is. So you pick a representative value. This interval comes out negative. Anything in this interval is positive, and this one's negative. So again, you can verify. Those are where the values of the domain lie. Okay, if you need a little refresher, I'll link a video here. I have one on how to solve quadratic and higher order inequalities. Okay, so domain is everything between but not including negative 2 rad 3 and 2 rad 3. Good? Beautiful. Okay, next step is we need to find our intercepts. Alrighty, so let's see here. We're going to have x-intercepts. X-intercepts come from setting y, or the function, equal to 0, which would mean 0 equals natural log of 12 minus x squared. How do you solve this equation? You rewrite it in exponential form. So remember, natural log, that's log base e, so this means e to the 0 is equal to 12 minus x squared. So 1 equals 12 minus x squared. X squared is equal to 11. So that means I have x equaling plus or minus rad 11 as my intercepts. Don't leave them like that. No, no, no. Always write intercepts as ordered pairs. Why is it such a big deal? Well, if you just leave it x equals plus or minus rad 11, x equals, that's the equation of a vertical line, right? And we're going to have asymptotes to check for in a hot second. So you want to make sure you're clearly distinguishing between what are points on your graph and what are asymptotes. All right, very nice. Now let's move on to the y-intercept. We get that by substituting 0 for x. So we have natural log of 12 minus 0 squared. So the y-intercept is ln of 12. All right, very nice. Should I leave it like that? No, only if I want to lose some points. So y-intercept is 0, natural log of 12. Like that. There we go. Box everything of significance. Fabulous. Now let's check for symmetry. So here we have y equals natural log of 12 minus x squared. If you want to rename this guy, this is f of x is natural log of 12 minus x squared. And when we're testing for symmetry, remember we evaluate f of negative x. So let's do it. So f of negative x, that's going to be natural log of 12 minus negative x squared. Since I'm raising negative x to an even exponent, it's just going to simplify back to x squared. And the result is the same as my original function f of x. So what does that tell me? It tells me my function is even. And even functions have y-axis symmetry. Oh, that's good to know. And it makes sense too, because look it, we already figured out the intercepts were at plus or minus rad 11, comma 0. So it seems like, ooh, things are already going to be symmetric about the y-axis. Indeed, they are. So it can save us time. We know exactly one half of the graph is going to be a mirror image of the other half over the y-axis. All right, step 4. It's asymptote time. My goodness. Okay, so let's see here. Now, I'm not going to consider any horizontal asymptotes. Why do I say such things? Well, look at our function. It's y equals natural log of 12 minus x squared, and the domain is restricted between negative 2 rad 3 and 2 rad 3. Remember, horizontal asymptotes have to do with end behavior, right? What the graph does in the long term, and you find them by taking the limit as x goes to plus or minus infinity. I can't do that in this case because my domain is restricted. I'm only allowed to live within negative 2 rad 3 and positive 2 rad 3. I can't even think about taking a limit to infinity or negative infinity. It's out of bounds. It goes out of the domain, so it's not happening. All I need to do is check for vertical asymptotes, and I'm going to investigate what's going on near the endpoints of the domain. So since we're not including negative 2 rad 3 or 2 rad 3, I'm going to look at these limits as one-sided limits. Okay, so our investigation begins. That means we're going to look at the limit as x approaches. Now be careful. So negative 2 rad 3, that's the lower bound for the domain. That means I have to approach from the right, from values larger than it, of natural log of 12 minus x squared. Okay, now let's see here. I know negative 2 rad 3, that's rad 12. If I'm approaching through values a little bit larger, okay, then that means when I square it, it's going to be closer to 0, so it won't be quite so large as 12 when I square it. Think of something close to negative 2 rad 3, but that is not as negative, so technically a little bit larger. This quantity is going to be approaching 0, but through positive values. And then this is where you need to think of what does the graph of natural log look like. Okay, just regular old natural log. So it goes through 1, 0. Hopefully that's burned in your brain. This is just y equals ln of x. And as x approaches 0 from the right, natural log is approaching negative infinity. So this limit is negative infinity. Okay? Good. And then same thing, now let's check the limit as x approaches 2 rad 3, the upper bound of the domain. This time I'm going to have to approach from the left-hand side of natural log of 12 minus x squared. Why the left-hand side? I can't approach from the right-hand side. That's outside of the domain. The graph doesn't live there. We're not allowed. Okay, so if you're approaching 2 rad 3 from the left, you're coming from values that are a wee bit smaller. So if I square them and I take 12 minus that number, it's going to be getting close to 0, but it's positive. So just like before, this is approaching 0 from the right. So again, this limit's going to be negative infinity. So that means for us, we have two vertical asymptotes at x equals plus or minus 2 rad 3. All right, how exciting. Now, let's move on to calculus time. We've done some calculus with the limits and finding the asymptotes, but now let's take some derivatives. So the fifth step, what I'm interested in is finding where the graph is increasing and decreasing. And I need f prime of x, or dy dx. I'll call the function f of x equals natural log of 12 minus x squared. So f prime of x, remember, if you take the derivative of ln of something, you put 1 over the something, and then by the chain rule, I have to multiply by the derivative of the something, the argument. This is the something. What's the derivative of 12 minus x squared? It's negative 2x. Boom. What a relaxing derivative that was, eh? So critical values come from two places. What are they? They come from where? F prime of x equals 0. That would mean the numerator, negative 2x equals 0. That would mean x equals 0. So I've got a critical value right there. Where else do critical values come from? They come from where f prime of x does not exist. In this case, that would mean the denominator is 0, which would mean x equals plus or minus 2 rad 3. But these are not going to be critical values because these are not elements of the domain. Remember, the domain is the open interval from negative 2 rad 3 to 2 rad 3. In fact, we have vertical asymptotes at x equals plus or minus 2 rad 3. So there's no way those can be critical points, okay? They're not on the graph. All right, so here's my number line for f prime. Be so careful because the graph only lives between negative 2 rad 3 and 2 rad 3. So I only have one critical value to test, which is at 0. So pick something just a smidge smaller than 0, but not smaller than negative 2 rad 3, right? You could test with, what's a nice number? How about negative 1, yeah? So then you're going to take natural log. Now we're plugging it in the derivative here. So if I test x equals negative 1, for example, the numerator is going to be positive. The denominator is also going to be positive. So that means the derivative is positive. So the function is increasing on that interval. Then say I want to test the next interval. Let's pick x equals positive 1. Okay, now look, if I plug in positive 1 for x, the numerator is negative, the denominator is positive, which means the derivative is negative in this interval. So the function is decreasing. Wow, wow, wow. What does that mean for us? Well, look what happens. The function goes from increasing to decreasing. So at x equals 0, we don't just have a critical value, we have a local max, yes. So local max at x equals 0, and let's give it as an ordered pair. So we got to find its partner in crime, the y value. We actually already have it. It's our y-intercept. So max at 0, natural log of 12. Okay. Things are shaping up nicely. Are you guys ready to keep going? All right, we need to investigate now concavity and inflection points. Oh yes, so concavity and inflection points, which means we need a second derivative. So f prime of x, if you'll remember, was negative 2x over 12 minus x squared. So f double prime, let's go. It's quotient rule time. Do you sing the song? We've got low, d high, derivative of the numerator is negative 2, minus high, d low, so derivative of the denominator, that's negative 2x, square the bottom, away you go. 12 minus x squared squared. All right, now we clean up the numerator. So I'm going to distribute the negative 2. We've got negative 24 plus 2x squared. Count up your negatives. I've got 1, 2, 3. Okay, so this term's going to stay negative 4x squared over 12 minus x squared squared. Okay, I notice I can combine some like terms. So I have negative 24 minus 2x squared over 12 minus x squared squared. And let me factor the GCF out of the numerator. I can take out a negative 2, and then I'm left with 12 plus x squared over 12 minus x squared squared. So this is f double prime. Do you notice something? Well, look, the denominator is always positive, right? Because I take 12 minus x squared and then I square it again. So this is always positive downstairs. 12 plus x squared, guess what? That's positive always too, because you're squaring x and then adding 12 to it. And then here's negative 2, just hanging out. So what does that tell me? I have a negative times a positive divided by a positive. This second derivative is always negative for all x's that are in the domain. That means there's no inflection points because the graph will not change concavity. In fact, the graph is always concave which way? Concave down. Don't say everywhere. No, no, no. You have to keep your wits about you right now. It's concave down everywhere the graph exists or where it lives on the domain. So it's concave down on negative 2 rad 3 to 2 rad 3. Okay, please be careful, careful, careful in situations like this to always consider what the domain of the function is. All right? So we've got no inflection points. It's concave down everywhere it lives. I think it's time to graph it, don't you? Here we go. As long as you label everything, you are good to go. So here's the x-axis, here's the y-axis. Please label your axes, especially if you have to go on to Calc 3 later on. They're going to switch up on you, okay? The graph lives between negative 2 rad 3 and 2 rad 3. In fact, that's where our asymptotes are. So I'm going to indicate that with dashed lines. Okay. We also need to include our intercepts. So we have a y-intercept at 0, natural log of 12. And you go, oh, this is ln of 12 because I said so. And then we have x-intercepts at plus or minus rad 11, comma 0. Same thing. You go, hello, this is negative rad 11. And hello, this is positive rad 11. Beautiful. Plot those guys. This also, don't forget, at 0, ln of 12 is a local max. And the graph is always concave down. So concave down means it has the same shape as a parabola that opens downward. In fact, this is going to look like a smashed parabola that is not allowed to extend forever. It goes down forever, but it can't open up in the x direction forever. It just lives between the two asymptotes. But I don't love this little wiggle. We have to make it as perfect as possible. Okay, how does your graph look? Do you have everything all labeled nicely? I hope so. This is 100% right here. If you do this on an exam, beautiful. All right, let's do some trig functions for a bit. So example 2. Here we go. We've got f of x equals sine of x over 1 plus cosine of x. All right, full steam ahead. Here we go. First step is the domain. Let's look here. This cannot be 0, which means cosine of x cannot equal -1. When does cosine equal -1? Bam, the unit circle should come straight to your mind. Cosine is -1 at all odd multiples of pi. What do I mean by that? Cosine equals -1 right here. That's pi, which is also coterminal with, if you spin around the unit circle again, 3 pi, which is coterminal with 5 pi, 7 pi. Or you could go backwards, right? Why not? Who's to stop us? -pi, -3 pi, etc., etc. So we have infinitely many points of discontinuity, or infinitely many points that we have to remove from the domain of this function. Do we sit there and list them all? No way, we couldn't do it. So you just say the domain is all x's such that x better not be an odd multiple of pi. How do I say an odd multiple? 2k plus 1 times pi, and then you tell everyone PS k is an integer, belongs to the set of integers. Okay, anytime you need an odd number, you can represent it with 2k plus 1 or 2k minus 1. Just think about it. If you take 2 times some number, that makes it even. You're doubling it. And then if you add 1 or subtract 1, then boom, it's odd. All right, and if k can be any integer, positive or negative, then we're good to go. Now I've encompassed all of the points I have to remove from the domain. Very nice. Okay, what about our intercepts? Okay, so x-intercept, we get that by setting the function equal to 0, which means the numerator would be 0. So when is sine of x equal to 0, but be careful, cosine x cannot equal -1? Because notice, sine of x is 0 here at all of the points we remove from the domain. So those aren't going to be intercepts. No. The only place where I'm going to get x-intercepts are over here when sine is 0 and cosine is +1, not -1. Ooh, so that's a little interesting. Let's see, that would be when x is 0 or 2 pi or 4 pi, etc., or -2 pi or -4 pi or -6 pi, etc. All the even multiples of pi. So that would be x equals 2 pi k, where k is an integer. So you have infinitely many. If you were to write it as an ordered pair, it would be 2 pi k, comma 0. Those are all of our x-intercepts. All right, what about y-intercept? Well, if I plug in 0 for x, f of 0 is equal to sine of 0 over 1 plus cosine 0. So that's 0 over 2, which is 0. So we have a y-intercept at 0, 0, which is covered in here if k is 0. So that's all taken care of. Okay. Good. Let's keep going. So step 3, we're going to check for symmetry. All right, so I'll remind you, f of x is sine of x divided by 1 plus cosine of x. So f of -x, that's going to be sine of -x over 1 plus cosine of -x. Now you should remember, All trig functions are odd except for cosine and secant. Just think cosine and his partner in crime. They're the even ones. So that means sine of negative x equals negative sine x, since sine is an odd function, over 1 plus cosine of x. Cosine's even, so it absorbs the negative, basically. And look at what we have here. This is the opposite. I can take that negative right here, pull it out, no problem. This is negative sine of x over 1 plus cosine of x. And lo and behold, this is the opposite of f of x, which tells me f of x is an odd function. That's the definition. All right, what does that mean? If it's an odd function, then we have origin symmetry. Okay, and if you remember much about graphing your trig functions, the period for sine and cosine is 2 pi. So this graph will have a period of 2 pi as well. If you didn't quite catch that, it's no problem, because look, we figured out where all the intercepts were. They keep coming every 2 pi. And then same thing here, the domain, we have to restrict all odd multiples of pi, but that repeats every 2 pi. So you should have picked up on the fact that the period of this graph is going to be 2 pi. All right, how are we doing? Hopefully you're not overwhelmed, although this one is intense, so it's okay. Let it marinate. Here we go. Step 4, we need our asymptotes. Okay, so like before, we cannot consider limits to infinity because we're not able to take such limits and investigate horizontal asymptotes with all of the discontinuities in the graph. So there's no horizontal asymptote. And if you want to think about the limit as x goes to infinity of sine x over 1 plus cosine x, this just does not exist. Both sine and cosine are periodic, right? And I can't bound this using some sort of squeeze theorem or anything. So this limit just doesn't exist. There's no horizontal asymptotes. I do want to investigate what's going on at all of the points that we have to remove from the domain. I want to investigate what's going on at all the odd multiples of pi. So what's happening when, or near x equals 2k plus 1 times pi. Okay, now I think the easiest way to do it is I'm just going to pick k to be a specific number. In this case, I'm just going to let k equal 0. Since it's periodic, whatever happens near one of the asymptotes is probably going to just keep repeating in the next one and the next one. Okay, so we're going to look at each side. That means I'm going to look at the limit as x approaches pi from the right of sine of x over 1 plus cosine of x. And then I'm also going to look at the limit as x approaches pi from the left of sine of x over 1 plus cosine of x. Okay, so now it's time to think of our unit circle again. So x is approaching pi from the right. That means from values larger than pi. So this is a little tricky. You're coming towards pi from values larger than pi. You're coming this way, okay? So that means sine of x is approaching 0, and cosine of x is approaching -1, so 1 plus cosine x is also approaching 0. So we have an indeterminate form of the type 0 over 0. So let's go ahead and apply L'Hopital's rule. Let's move this out of the way. Always indicate that you're using L'Hopital's rule. Throw a little h over there. So we've got the limit, x approaches pi from the right. Derivative of the numerator is going to be positive cosine x. Derivative of the denominator is negative sine x. Okay. So as x approaches pi from the right, that means cosine of x is approaching -1, and then negative sine of x. So sine of x is approaching 0 through negative values, but then I have this other negative in front of it. So the denominator is approaching 0 through positive values. What does this mean for us? The numerator is approaching a negative constant. The denominator is shrinking. Whenever this happens, that means the whole expression is blowing up and getting bigger and bigger. Think of it. The denominator is getting tiny, tiny, tiny. So you're dividing by something getting smaller, smaller, smaller. So the whole thing's getting really, really large in the negative direction because I have a negative numerator and a positive denominator. So this limit is equal to -infinity. All right, that can be tricky. You got to think about it carefully. 0 over 0 is an indeterminate form, but if you have a non-zero constant divided by a denominator that's approaching 0 and you can determine the sign of the expression, then your limit's either going to be positive infinity or negative infinity. Okay, so in this case, when we're approaching pi from the right, the limit is -infinity. Okay, what about the other side? So now we're going to look at the limit as x approaches pi from the left. Okay, again, at this step, the numerator is approaching 0. Denominator is approaching 0. So let's apply L'Hopital's rule. So we've got the limit, x approaches pi from the left of cosine x over negative sine x. So again, cosine is approaching -1. However, this time we're approaching pi from the left, so from values smaller than pi. But be careful, when you look at your unit circle, values smaller than pi are from this way, yes? And notice we're above the x-axis, that means y values are positive, so sine of x is positive there. So as we are getting closer and closer to pi, sine of x is approaching 0, but through positive values. So this right here is going to 0 through positive values, but then I got that extra negative over there. So the denominator is approaching 0 through negative values. Whew, okay. Similar to the last limit that we took, except since I have a negative constant in the numerator and the sign of the denominator is negative, those two negatives cancel out and this limit's going to be positive infinity. Denominator shrinking, numerator is approaching a non-zero constant. That means the whole thing's blowing up. You might need to review your limits, your infinite limits from previous lessons if this is a little rusty for you. Okay? So we got our asymptotes down, and this is going to be true for all odd multiples of pi. So we can just repeat this process when we're graphing, and we're going to have all of these asymptotes being the same. So if you were to approach 3 pi from the right, the limit would be -infinity, and then 3 pi from the left, it's going to be positive infinity. Okay, now increasing, decreasing. Have I been numbering or lettering things? Numbering. Okay, so step 5, increasing, decreasing. It's time to take a derivative. Maybe that's going to seem relaxing after all this. Who's to say? So f of x is sine of x over 1 plus cosine of x. Quotient rule time again. So f prime of x is low, d high, derivative of the numerator is just cosine x, minus high, d low. Derivative of the denominator is going to be negative sine x over low, low. So 1 plus cosine x squared. All right, we're going to distribute up a storm here. We've got 1 plus cosine squared x plus sine squared x over 1 plus cosine of x squared. This should just be screaming at you. Cosine squared plus sine squared is 1. Very good. Oh, you know what? I distributed wrong, didn't I? Heavens to Betsy. That's cosine x. Okay, I got too excited. So we've got cosine x plus 1 over 1 plus cosine of x squared. Ooh, this is much more exciting because now look at this. 1 plus cosine x cancels with one of the factors of 1 plus cosine x in the denominator there. And we have 1 over 1 plus cosine x. Voila, this is f prime of x. All right, now let's get our critical values. So critical values come from two places. Have you memorized this by now? I hope so. First place, where f prime of x equals 0. That would mean the numerator equals 0. That's not happening. The numerator is 1. It's a constant. It can't be 0. All right, other place is where f prime of x does not exist, which would be where cosine of x equals -1. But all of those places are not in the domain of the original. So again, there's none. We actually have no critical values. What to do? Well, we still want to see if the graph is increasing or decreasing. So let's make a number line and we're just going to test it. Be careful. Remember, all of the odd multiples of pi are not in the domain. So I'm going to list a few of them out. All right. So we've got negative pi, pi, and 3 pi. And that's good. Let's see what's going on here. And I can test in between, maybe with x equals 0 and x equals 2 pi into the derivative and see what's going on. Okay? So if I test with 0, f prime of 0 is going to be 1 over 1 plus 1, so that's positive. So if the derivative is positive here, that means my function is increasing. And guess what, people? Same thing at x equals 2 pi, and same thing if you were to test 4 pi, so on and so forth. That means wherever the function exists, wherever the function is allowed to live, it's always increasing. Okay? It's increasing. Now you got to be careful how you write this out, because are you going to sit here and list out every single interval? I don't think so, right? So it's increasing from pi to 3 pi, and then union 3 pi to 5 pi, union 5 pi to 7 pi, etc. And you can just write that out by saying it's increasing from 2k plus 1, or let's go 2k minus 1 to 2k plus 1, each of those times pi. Let me scoot this over. I forgot to write the pi. So 2k minus 1 times pi to 2k plus 1 times pi, where k is an integer. So what does this mean? Okay, well, if you let k be any integer, these are always going to be 2 apart, right? Just like pi and 3 pi, those are 2 pi apart. 3 pi and 5 pi are 2 pi apart. And I'm guaranteeing that these are always going to be odd integers. So 2k minus 1 is always going to be the odd integer that comes before 2k plus 1. All right, so this is where it's increasing. Beautiful. What about concavity? And let's just state there's no extreme values, so no one worries we didn't think about it. Okay, concavity time, inflection point time, all that good stuff. So this is step am I on? 6, step 6. Concavity and inflection points. So I need f double prime. If you'll remember, f prime of x was 1 over 1 plus cosine of x, which you could think of as 1 plus cosine x to the negative first, right? That's going to make it easier. Now I don't have to do the quotient rule. I can just use the power rule and the chain rule. So f double prime of x is going to be negative. Leave the stuff in the parentheses alone. Subtract 1 from the exponent. Now I have 1 plus cosine x, and then by the chain rule, I multiply by the derivative of 1 plus cosine x, which is negative sine x. Now let's clean this up. So those two negatives are going to cancel, so I have sine of x over 1 plus cosine of x squared. Okay? Now let's see here. This second derivative, I notice the denominator is squared, so it's always positive, except for where it doesn't exist, but those aren't points in the domain, which means that f double prime is positive when sine of x is positive, and f double prime is negative when sine of x is negative. Okay, so the graph is going to be concave up whenever sine is positive. So think, when is the unit circle above the x-axis? From 0 to pi, and from 2 pi to 3 pi, and from 4 pi to 5 pi, and you can clearly see we got to figure out a better way to write this out so we can finish the problem in our lifetime. So the lower bound of each interval is an even multiple of pi. So that's going to be at 2k pi. Then the upper bound is an odd multiple of pi. So you're going to take 2k plus 1 times pi, where k belongs to the set of integers, z. That's where it's concave up. Now, where is the graph concave down? It's concave down everywhere sine is negative. So imagine your unit circle. Sine matches the y values on that unit circle. So when is the unit circle below the x-axis? From pi to 2 pi, and then from 3 pi to 4 pi. I'm just listing out some so we can get the pattern, you see? And then again from 5 pi to 6 pi, etc. So that means it starts at an odd integer. So we can start at 2k plus 1, but it's better since we're going to bump it up in the next one. I'm going to start at 2k minus 1 times pi, and then the next one would be 2k pi, where k is an integer. Okay, if you started with 2k plus 1, then you would have to add extra to make sure this is even and it looks less clean. Okay. Whew, we survived. That was tricky if you're not used to doing it, for sure. Let's box them with pride. That took some thinking. Okay, so that means we do have changes in concavity. So we have inflection points. Oh my goodness, yes we do. Where does the change in concavity happen? Whenever x is equal to 2k pi. All the even multiples of pi. Why not the odd multiples of pi? You tell me. Why aren't those inflection points? They're not in the domain. Very good. Okay. So those are the x values where we have inflection points. What's the y value going to be? Do you even remember what the original equation was? My goodness, it seems like ages ago. So it was f of x equals sine of x over 1 plus cosine of x. So that means f of 2k pi is sine of 2k pi over 1 plus cosine 2k pi. I don't even care what the denominator is. Sine of any even multiple of pi is going to be 0. I know the denominator is not going to be 0 because we took all of the odd multiples of pi out of the domain, so we're safe. Whew! So here's our inflection points, 2k pi, comma 0. Shall we put the graph together? This is a fancy one. Definitely fancy. Here we go. We'll do like 3 periods. That way we feel as if we've covered enough of the interesting facets. check with your instructor what they would want, okay? Always strive to make them happy. Here we go. So x-axis, y-axis. We've got asymptotes, every odd multiple of pi. So here's 1 pi. All right, this is 2 pi. This is 3 pi. This is negative pi, negative 2 pi, negative 3 pi. So asymptotes are at all of the odd multiples of pi. Bam. Another one. Another one. DJ Khaled. Okay, then we've got inflection points at 2k pi 0. So that means here at 2 pi, we've got an inflection point. We've got another one here. Actually, that's our intercept, right? Our x and y intercept 0, 0. Do you remember we found that so long ago? Here's another inflection point. So this is at 2 pi, that's 0, negative 2 pi. It's always increasing. Did you remember that? The graph is always increasing. And then you can check back on our concavity. Okay, so it's concave up from 2k pi to 2k plus 1 pi. That means it's concave up in between here, and it's concave down over here. Also remember, we got our limits. We know that the limit as we approach pi from the right is negative infinity, and as we approach pi from the left, it's positive infinity, and that repeats. So maybe you kind of already have a feel for what it's going to look like. Yes, it almost looks like our good friend tangent. Don't you think? Wow, wow, wow. Beautiful. And that's really all you can say about it. That one took a lot of work. If you're tired, that's okay. I'm exhausted too. I've got one more to do for you, okay, with an exponential function. And then I think we can call it. So example 3. Are we ready? F of x equals 1 over 1 plus e to the negative x. Ooh, all right, so here we go. First and foremost, the domain. Okay. Will the denominator ever equal 0? E to the negative x, that's never going to be 0. So the domain's all real numbers, negative infinity to infinity. Step 2. What do we have to do for step 2? We have to figure out the intercepts. Okay, lovely. So x-intercept comes from setting the function equal to 0, which would mean the numerator equals 0. There isn't one. The numerator's 1. Y-intercept, if I plug in 0 for x, let's see what happens. F of 0 is 1 over 1 plus e to the negative 0. That's just going to be 1 also, so this is 1/2. Okay, how lovely. 0, 1/2. All right, step 3, symmetry. Do we have any? So f of negative x is 1 over 1 plus e to the negative x. So that's 1 over 1 plus e to the x. Well, this does not equal my original function, nor does it equal the opposite of the original. So that means it's not even, it's not odd, there's no symmetry. All right, it's worth checking, especially if your teacher gives you points for it. Okay, next, asymptotes. So the domain's all real numbers. That means there's going to be no vertical asymptotes. But this time I'm going to check for horizontal asymptotes. All right? Ooh, this is exciting. So let's check the limit as x goes to positive infinity of 1 over 1 plus e to the negative x. So as x goes to positive infinity, this is what I want you to think of. Whenever you have e raised to some negative exponent, right? That's the same as 1 over e to the x. So if x is getting really, really big, e to the x is also getting really, really big. which means 1 over e to the x is going to 0. So this limit's going to be 1 over 1 plus 0, which is 1. All right, now what about the limit as x approaches negative infinity? Now we have 1 over 1 plus e to the negative x. But if x is going to negative infinity means this term right here is blowing up. This is going now to positive infinity. The numerator is a constant. The denominator is getting huge. You're dividing by something getting bigger and bigger and bigger. So this is going to 0. So this is fun because we have two different horizontal asymptotes. So when you go in the positive x direction, the horizontal asymptote is at y equals 1. And then when you go in the negative x direction, the horizontal asymptote is at y equals 0. Ooh, so snazzy. Okay, derivative time. Increasing, decreasing, all that good stuff. So step 5, we need increasing, decreasing. So let's look at our function. It's 1 over 1 plus e to the negative x. Okay, you don't need to do the quotient rule. Why do I say that? There's no variables in the numerator. So please rewrite this as 1 plus e to the negative x to the negative first. Now let's go ahead and take the derivative. So f prime of x is going to be negative. Leave those blank parentheses, subtract 1 from the exponent. Then rewrite whatever was there originally. Don't touch it. 1 plus e to the negative x. And then you use the chain rule. You're going to multiply by the derivative of what's inside of 1 plus e to the negative x. So what's the derivative of that? It's going to be negative e to the negative x. Good? All right, clean this up. So the two negatives are going to cancel. I have e to the negative x over 1 plus e to the negative x squared. All right, let's see about critical values. They come from two places where f prime of x equals 0. That would mean e to the negative x equals 0. That's impossible, right? Our exponential functions do not equal 0. So there's none there. Other place where we get critical values is where f prime of x does not exist. That would mean 1 plus e to the negative x squared equals 0, which would mean e to the negative x is negative 1. Again, that's not possible. So there's no critical values. In fact, did you notice something? Look at the denominator. It's always positive. And e to the negative x, great, hopefully you remember your exponential graphs, otherwise we're in big trouble, guys. So e to the x looks like this, e to the negative x has just been reflected. Again, that's also positive. So that means the first derivative is always positive. So f of x is increasing where on its domain? What's its domain? All real numbers. Wow, so there's no local extrema. Nope. Or absolute extrema either, for that matter. All right. So I answered that question. I think that's step 6. Now let's do concavity and inflection points. All right. So we need f double prime. So f prime of x, let me rewrite it for you, was e to the negative x over 1 plus e to the negative x squared. So let's take another derivative. Here we go. Ooh, we gotta be careful. So we've got low, d high. So derivative of the numerator is gonna be negative e to the negative x minus high, so e to the negative x, d low. So 2 times 1 plus e to the negative x times negative e to the negative x. Use the chain rule. Over low. 1 plus e to the negative x to the 4th. All right, how do you clean this up and keep your wits about you? You factor out the GCF, people. Yes, you do. So what do I notice? I've got negative e to the negative x in both the terms. Fantastic. We're factoring it out. Negative e to the negative x. What else can I factor out? I can take out 1 plus e to the negative x. I can take out one of them. So let's do it. 1 plus e to the negative x. Can I take out anything else? No, I'm so sorry, we cannot. Okay, so what is left over? I've got one of these 1 plus e to the negative x's left. And then I've got a negative e to the negative x times 2. Negative 2e to the negative x. All right, over 1 plus e to the negative x to the 4th. Did you make it? You have to be so careful when you're using the quotient rule, especially for second derivatives, that you clean it up correctly. My goodness, what if we made a mistake? Okay, so 1 plus e to the negative x, I can cancel out one of those. Yay. And let's see, anything else exciting? We've got negative e to the negative x times, these are like terms, right? So this is 1 minus e to the negative x over 1 plus e to the negative x cubed. If you want to get rid of this negative here, you could just reverse the order of subtraction, because then that's going to give us another negative 1. That's optional, but mine doesn't make it look better, huh? So let's do it. Oh yes, what a second derivative. Now I love it. 1 plus e to the negative x cubed. Okay, we're going to box this bad boy. Here we go. So, possible inflection points. I want to look, where does f double prime equal 0? So that would mean e to the negative x is 0. We've talked about the fact that that can't happen. Or e to the negative x minus 1 is 0. Ooh, that means e to the negative x is 1. That means x is equal to 0. Yeah? If you need to, you could just take the natural log of both sides. Ln e to the negative x is ln of 1. Negative x is 0. X is 0. Good? Fantastic. Other place where we get critical values is where f double prime of x does not exist. That would mean the denominator is 0. I don't need the cubed part. But again, this is not going to be possible. E to the negative x equaling negative 1. Nope, not going to happen. So I only have one possible inflection point at x equals 0. Ooh, exciting. So let's test on our number line. Here's f double prime. Here's x equals 0. Always label the number line that way. When you're testing, you know where to plug it in. It's a good reminder, right? Like, oh, I labeled it f double prime. So say I'm going to test with x equals negative 1, and I'm sure by now you're overwhelmed with all this math, and you're like, oh, where do I plug it in? You plug it into f double prime. Yes. All right. So I know e to the negative 1, that's e. So 2.7-ish minus 1, that's going to be positive. I know this guy's always positive, and this is also always going to be positive. So the second derivative is positive here, which means the graph is concave up. Hooray! What about for something bigger than 0? So say you plug in 1. Does that sound good? Sure, why not? So if we test with x equals 1 in the second derivative, I know the denominator is always positive. E to the negative x is positive. E to the negative first, 1 over e, it's about 0.4. It's smaller than 1 is what matters, okay? So this is negative right here. so the second derivative is going to be negative, so it's concave down. Wow, what does that mean for us? We've got an inflection point right here, people. Yes, so we've got an inflection point when x is 0. And actually, we already figured out this was our y-intercept, f of 0, which is 1/2. Okay, let's put it all together. This is the most exciting part. Don't be scared. A lot of the time students, they get so nervous to put everything together and make the graph, but you should think of it as like the final reveal. It's very exciting. Just use all the steps that you have, right? So we found our intercept, 0, 1/2, and then we've got our asymptotes at 1 and 0. So watch, I'm gonna put both of them in, but remember, as x approaches positive infinity, the graph approaches 1, and then as x approaches negative infinity, it approaches 0. Okay, it's concave up from negative infinity to 0. So over here, it looks like a concave up. So imagine like your parabola looks like this, right? And the other thing is we figured out that it's always increasing. So the shape, how are we going to make it work? Well, the shape is going to be concave up, going up, 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 up. And then it switches to concave down because this is an inflection point right here. Keeps increasing, and there's the other asymptote. See, what a friendly little graph, nothing to be scared of. Anyways, I hope this was super helpful to you guys. Make sure you're patient with yourself, but you're also meticulous and like a little calculus beast when you do these problems. They're not for the faint of heart, so you really got to like turn it on and make sure you're there to get them right. Okay, please give the video a thumbs up if you found it helpful or you like this. Share it with your classmates. I'd love it if you would subscribe and stay tuned. I'm happy to take more video requests, so if there's anything you'd like to see, message me, comment down below, and I will do my best to make a video for you ASAP. Happy studying!